Okay, so here's kind of the plan for the next 3 days. Today's Monday, the last day in February. Cry. Yeah, because February's almost over. So if you've done diddly squat in February, today's your last day to make up for it, right? Tomorrow is the first day of March. We call it March 1st or March Day. Okay. Yeah, I made that up. Now, we're going to review tomorrow. So example 6, we're going to do on tomorrow because we're going to review tomorrow. Review Tuesday, review on Tuesday, and we'll start with example 6 for review. And then we're going to test on Wednesday.
Serious?
Yeah, because that's March 2nd. That's the second. It's an even day. But what? We're not going to test over butts, okay? No, no, that's too long away. We got other plans. So it's going to be 5.1 through 5.3, heavy on the 2 clues problems, okay? That's going to be like your, like the quiz will be like your free response, okay? And we'll review that tomorrow. So today I want to start the unit circle. I usually do the unit circle in one day, and sometimes it's too much for people to, take in one day. So today I'm just going to ease you into the unit circle, all right? That's what today is. So tomorrow we'll review, start with example 6, work another 2 clues problem, and then we'll test on Wednesday. All right, so this is the unit circle. Whoa. And this thing is super important for the rest of this semester and even on into calculus and beyond. This becomes like your multiplication tables. Remember when you were learning arithmetic, you had to memorize your multiplication tables? And I don't know how I made the mistake of telling people earlier, you memorized them by practicing and making flashcards, and like, we never did that. But you know your multiplication tables, right? 4 times 2, you have to think about it. It's 9, right? Minus 1, right? You know that, right? Oh, yeah. And 8 times 7, 8 times 7, right?
We did a song.
56. You did a song about 8 times 7?
We would sing like the.
Oh, 1 times 1 is 1. No. 1 times 2 is 2.
So like
1 times 3 is 3. 1 times 4 is 4. It's a great song.
We would all sing. No, we would go 7.
Okay. Well, here's the deal. Here's what I'm trying. The point I'm trying to make is right now when I say what's 9 times 6, you know exactly what it is, right? 54. You don't have to think much about it hardly at all, right? This right here is going to become part of your reflexive knowledge. I'm going to say something like, what is cosecant of 11 pi 6? And you're going to say it's -2. Okay. Yeah, eventually you're going to know that. So we're going to derive this. We're going to develop it from the ground up. You're going to know what all these numbers mean, where they come from, and it's going to make it easier for you to use. Okay. And then we're going to quiz on it every day for like the rest of the year. Okay. No, I'm not kidding. All right. If we can stay out of the war, we will. And thank goodness we're not, we don't have to worry about a missile hitting us right now, right? Because people right now in Ukraine are clamoring to get onto a train to get out of there, and there's only limited spaces, and men that are aged, 25 to 60, they're not even allowed to leave, or 18 to 60. Yeah. Oh, I don't know. Oh, yeah, because Putin kind of upgraded his nuclear, he's mobilized his nuclear arms. So anyway, yeah, Weaver. So let's hope we're testing on Wednesday and learning unit circle after that, right? So what I guess, thank you for agreeing. Yes. All right. Yeah. All right. So to do this, let's insert a new page, right? I want to tell you what the unit circle is first. So let's start off with the definition. A unit circle is, first of all, a square, right? I'm kidding. It's a circle, right? That's centered at the origin. It's centered at the origin, whose radius is 1 unit. And that unit could be anything: inches, meters, bananas, tanks, football fields, stadia, whatever. It's 1 unit long, okay? So why would be interested in what all these numbers? Well, I'm going to kind of work backwards. What this does is it gives us a way to quickly get the 6 trig functions for very common angles. And if you look at the angles that are on here, we have 30, 45, 60, and then, bless you, and then multiples of those all the way around, multiples of those all the way around. And we're going to be able to then figure out what the sine and cosine and tangent and their reciprocals are very quickly just by knowing a very limited number of things, okay? So this gives us the trig ratios for common angles. That's essentially what it is. So let's start with some of those triangles from geometry. You had your special right triangles, if you remember from geometry. Special right triangles. What were they? They were special. Do you know what they were? Or do you know why they were special? Because they were what? They were right. When they were born, their parents told them they were special and they believed them. I'm trying to do this with straight lines like snap features, and I can't do that. It takes too long, right? Can y'all do that? I'm not good at it. Believe in myself. I can do it. Okay. I can do it. Sisu, baby. We might run out of time, but we could persist, right? Ah, come on. Why does it not snap? Am I shaking it too much or? Oh, they have to? Okay. Oh, and then it'll make a triangle for you. Ah, see, right. Okay. But I'll try that. I'll try that. Okay. So this was your 30, 60, 90 triangle, if you remember that. It's a scaling triangle, and the special one is 30 and 60, okay? So remember, the sum of all the angles in a triangle in Euclidean space have to add up to 180, right? So if one of them is 90 degrees, the other two have to add up to 90 degrees, right? Like 30 plus 60. What do we call two angles that add up to 90 degrees? Complementary. Very good. Complementary. The easy way to remember it is because if they're complementary, they add up to 90, which means they both have to be acute, right? So imagine one of them saying, "Yo, you acute, buddy," and the other one saying, "Ah, thanks, you acute too. You're so complimentary." All right. That's one way to remember it. Okay. And then the other special right triangle was your isosceles right triangle. Ah, it didn't work. Hey, I did it. Lo hicimos. Yo hago. I think that's how you say it. I don't know, past tense. It's been a while. This is your 45, 90, right? It was your isosceles, okay? Now, the reason these were special is, did anyone remember, or were we all told why they were special for reals? What? Well, why was your 20, 70, 90 triangle not special? Because 20 plus 70 was 90, right? You never studied your 20, 70, 90 triangle, did you? That wasn't special. The reason these are special, well, they're both acute. Yeah, very acute.
Because of the math involved.
The math involved is simple. Yeah, that kind of hits on it a little bit. It goes back to the sexagesimal number system and sexy numbers, which I think is what York was getting at, right? When he says the math involved is simple, he's saying, hey, these are not just special right triangles, they're sexy right triangles, okay? 30, 60, and 45s are all factors of 360, right? They all go into 360 evenly, and they themselves have lots of nice integer factors. So we can build up from here, and we can partition down from here pretty easily, all right? So we can build other triangles from them. Now, the way that you typically label the side lengths is this. This is typically what we do. In general, people don't like fractions, right? Yucky, yucky, gross, gross. So you label the smallest side with a unit length of 1. So I'm going to start with the 45, 45, 90. Your unit length is 1. And then by the Pythagorean theorem, you could build up easily the hypotenuse to be the square root of 2. Beautiful. It is beautiful. It's actually so beautiful, Hypasus got murdered for it, okay? I think I told you that story earlier in the year. Hypasus let out the this triangle to the world, that the square root of 2 is not a rational number, and the Pythagoreans took in fishing, remember, and threw them overboard with concrete shoes.
Oh.
Yeah.
No, we heard about the beach one.
The beach. Oh, I'll tell you the more the details later on. But someone actually died for knowing about this triangle, right? And y'all are safe. Y'all can spread this at lunch all over the place, like COVID without masks. You know, yeah, just spread it, right? And everyone's going to be safe, right? Because this is common knowledge now. We know the square root of 2 is irrational. And then over here, the way this works when it's scalene and all the sides are different is we label the smallest side a unit length of 1. So opposite the smallest angle is the smallest side. You remember that? So opposite the 30-degree angle is the smallest side. We'll call that 1. Now, you can't really come up with the other side lengths here unless you do a little trig. So I always remembered it as 1, 2, square root of 3. It's kind of like counting 1, 2, 3, 1, 2, but then you put a square root of 3 at the end. But you do have to know that 2 is the hypotenuse because 2 is larger than 1 and 2 is larger than the square root of 3. So this is your 1, 2, square root of 3 triangle. And from here, you can get all kinds of bigger or smaller triangles by multiplying or dividing each side by a scale factor, right? So if you want to make it twice as big, multiply all 3 sides by 2. If you want to make it half as big, divide each side by 2, right? Remember that? Okay. So what we want to do is we want to put these guys onto the unit circle. All right. So what we're going to do is we're going to scale the hypotenuse. We're going to scale the hypotenuse, which is going to end up being the radius on the unit circle, to 1 unit. Okay, that's our goal. And right now we have a 2 and a square root of 2. Now, before I get too far into there, let's just review a little bit of Sohcahtoa, okay? So if we come down here, let's look at that 30, 60, 90. What would the cosine of 30 degrees be? Well, because we're not on the coordinate plane, we can go back to Sohcahtoa. It's adjacent over the hypotenuse, which would be what? What's the adjacent to 30? No, well, that's the adjacent, but it's the longest adjacent. There's always 2 adjacent sides, and one of them is always the hypotenuse. So when we say adjacent, we really mean non-hypotenusal adjacent, right? But that's too much to say. So it's the square root of 3 over the hypotenuse, which is the longest adjacent side. Yeah, 2. And then what would the sine of 30 degrees be? Well, that's so opposite over hypotenuse, it would be 1 over 2. Yeah. The cosine of 30 degrees is square root of 3 over 2, and the sine of 30 degrees is 1 over 2. Got it? Okay. I just wanted to review that. And we had to use Sohcahtoa there because we're not on the coordinate plane. All right, so now let's go ahead and scale our hypotenuse to 1 unit. Why? Because the hypotenuse becomes the radius of rotation on the unit circle. And if you remember, I said the radius, which if you want to put here, the hypotenuse, is the same thing. They're interchangeable here, is 1 unit. So let's do it for the 30, 60, 90 first. I'm going to copy this down below. Copy, paste, so much nicer than having to redraw it. All right, now what do I do to make my hypotenuse 1 unit long? I can't subtract 1 because it has to be a scale factor. I can either multiply or divide. Divide by 2. Good. So if I divide this by 2, I got to divide all the sides by 2, right? And what does that give me? That gives me a 1, 1/2, and a square root of 3/2. Okay. It gives me a 1 and a 1/2 and a square root of 3/2. So what this does now is instead of making the smallest side 1 unit and building up from there without fractions, we're making the longest side 1 unit long. And then everything else now, since it's smaller, is going to be a fraction, right? And this is why we don't really teach it this way, because students don't like fractions. But we're okay with fractions now, right? Fractions are numbers too, right? What?
We don't discriminate here.
Let's try cosine of 30 degrees now. You think it's going to make a difference that we made it smaller? It's half as big. Do you think the cosine changes? No, it's adjacent over hypotenuse. And now the adjacent is square root of 3/2 divided by, guess what the hypotenuse is? 1. And anything divided by 1 is itself. So it's still the square root of 3/2. If I had made the triangle 5 times bigger, it would still be 5 times the adjacent over the 5 times the hypotenuse, and the scale factor of 5 would divide out. So this is what's cool about what we're going to do. Guess what the cosine of 30 degrees always is? Never, not always. Thank you. Very good. Yeah, wasn't a trick question. Right now in Ukraine, guess what the cosine of 30 degrees is? Square root of 3/2. Right now in Putin's billion-dollar palace, guess what the cosine of 30 degrees is? Well, I think it's whatever Putin says. But if he wants to be right, he's going to say square root of 3/2.
What if we just said square root of 1/2?
What? Square root of 1/2/2 is a fourth. Okay. Anyway, let's do sine of 30 degrees instead of cosine of 30 degrees. Well, that's opposite over hypotenuse. Guess what sine of 30 degrees is? 1/2 over 1, which is 1/2. That's the same thing we got up above. So there you go. Guess what sine of 30 degrees is right now in Joe Biden's bathroom? 0.5. Right. 0.5. You think Biden remembers that? No, man. No, man. Come on, man. But whether he remembers it or not, it's still 0.5. It's still 1/2. Sine of 30 degrees is 1/2. Guess what sine of 30 degrees was last Wednesday night when Ethan was doing his performance on stage and Teresa was watching, and vice versa. And so was Brett. It was 1/2. Did it come up in any of their acts? No. Okay. Everyone already knew it. Okay, now let's do the same thing here with the other guy. Let's take the 45, 90, copy it, paste it down here. And now I want to make the hypotenuse a 1. What do I have to do to all 3 sides to make that a 1? Divide by the square root of 2, right? Yeah, anything divided by itself is 1. So now I get a 1 over here, and I get a 1 over the square root of 2 for both of the other sides. Now, here's where rationalizing comes in. Notice the one we did over here, the denominators were really nice numbers. They were 2s. Square root of 3/2, 1/2. The reason we're scaling the hypotenuses to be the same is because we're going to put those on the same unit circle where the radius has to be 1. It would be nice if we can match up other things as well. So is there a way to take 1 over the square root of 2? Oops, let me write it over here to the side and get the denominator to A, not have a radical, and B, have a 2 instead? Yes, let's rationalize. Multiplying by the square root of 2/2, we get square root of 2/2. So that's another version of 1 over the square root of 2. They're exactly the same. That's the version that we're going to use because it puts the denominators in the same format as the other one. And we want things to be as easy as possible for ourselves. So now when we put these 2 triangles on a unit circle, the denominators are all going to be 2. Okay. So far, so good, right? We've just taken the 2 special right triangles. We've scaled the hypotenuses down, the longest side to 1, and the other sides are now fractions. We're going to look at just the 30 degrees today, but what we do for 30 degrees is going to work for 60, it's going to work for 45, and it's going to work for all 6 trig functions. Today, we're just going to focus on the cosine and the sine, all right? All right, so here's what we're going to do. Come back to this picture here. We're going to look at all of the triangles on the unit circle that have a 30-degree reference angle. So you could do it this way. We're kind of marking this up. If you look at all the angles that have 30-degree reference angles, of course, 30 degrees is one of them, 150 is another one, 210 and 330. Why are those all the ones that have 30-degree reference angles? Well, draw a straight line from that one blue point through the center to the other blue point, and then do it again over here. Draw a straight line straight across, okay? If you then drop the perp down all the way to the other side from one quadrant to another, you get what looks a lot like a bow tie. See that? Let's kind of color it. We can color it blue. Blue bow tie. Yum. What flavor is this? Blue? I love it. Is it blueberry? No, it's boysenberry. Oh, you ever tried that? When you go to IHOP, they have the syrup sitting out from 3 years ago. One of them is boysenberry. It's all sticky, and you're like,
What flavor is boysenberry?
It's boysenberry. You ever had boysenberry straight off the vine? No, I haven't either. All right, look, so there it is. Now, what this is watch. If you look at this angle here, and this angle here, and this angle in here, and this angle here, guess what each of those angles is? 30 degrees, 30 degrees, 30 degrees, 30 degrees. Each of those reference angles is 30 degrees. Yep, that's pretty cool. So that means all of those triangles are actually congruent with each other. If you take this triangle in quadrant 1 and reflect it across the y-axis, you get this one over here. And then if you take that one and reflect it down into quadrant 3, you get that one there. And then you reflect that one across the y-axis, or the first one across the x-axis, and you get that one. So it turns out that when we look at our 30 degrees reference angle, and later our 45 and our 60, there's always going to be 4 triangles that have the exact same reference angle around the unit circle, okay? And they're all congruent to each other. Remember what congruent means? They all have the same angles, but more importantly, in this case, they all have the same side lengths. They all have the exact same side lengths. Let's go ahead and label the side length each time. Let's start with our 30-degree reference angle in quadrant 1. Now, the 30-degree angle in quadrant 1, I'm going to write it out here because I kind of covered it up. The angle itself is 30 degrees, right? I'm going to put the angle out there. If you rotate 30 degrees, it's in quadrant 1, and because it's positive and already acute, it's also the reference angle. If I draw that up here, let's do it ourselves here. Wait, where was I? Yeah, let's do it ourselves. Let's give ourselves a, I don't want to muck up that other one too much. There's so much writing on there. This will help us kind of isolate the information. Give yourself an X and Y axis, and then you can give yourself a circle, right, on that axis. And I think it'll snap to it. Yeah. And then you can kind of fill it out. You can kind of move it left and right or up and down, so it kind of, matches. There it is. It looks pretty good. All right, now let's go ahead and draw our 30-degree triangle again, because that's the one I'm going to look at. So I got 30, 60, 90. Here's 30 degrees. Here's 60 degrees. And then here's 90 degrees. All right, I'm going to move it up here a little bit, get it out of the way. All right, so let's label the side lengths that we have, so there's not much clutter there. This was the square root of 3 over 2. This was 1/2, and this was 1, okay? We're going to look at the 30-degree angle. Now, if you want to draw them on our unit circle that we're making, the easiest way to draw them, instead of doing them one at a time, is just to draw a line through the center from one point on the circle and let it snap. Right, so kind of pick a point there, and then try to pick a point that's about the same place on the other side and snap it through the center. Let them intersect at the same place to the other side of the circle. In other words, make your own bow tie, and then drop it straight down. Make it snap if you can. Ooh, snappy bow tie. Boom, snappy bow tie. All right. And now we've created it. So I'm not going to shade it, but you can see them. All right. So let's look at the quadrant 1. I've got the side length of the square root of 3 over 2, and I've got the height of 1/2, and I've got the hypotenuse to be 1. Okay. And of course, this is 30 degrees right here. Boom. So what I'm going to do is I'm going to put out here this point now that intersects the terminal ray on the circle. That has a coordinate. I'm going to put the angle out there first. So the angle that lands there in quadrant 1, whose reference angle is 30 degrees, is also 30 degrees. What is the ordered pair? How would I get to that point as an ordered pair? Well, from the origin, I would have to go right, the square root of 3/2 units, and then I would go up 1/2 unit. Yes? Okay. And the hypotenuse is 1. So that is the ordered pair. Now, square root of 3/2 and 1/2. Does that ring a bell? Have we looked at that? What would the cosine of 30 degrees be? Well, just look at the picture. The cosine of 30 degrees is x over r. That's the square root of 3/2 over 1, which is square root of 3/2. That's the x coordinate. What's the sine of 30 degrees? Well, it's y over r. That's 1/2 over 1, which is a half. Guess what? That's the y coordinate. Holy moly smokers. So look at this. Cosine of theta we know is x over r, and sine of theta is y over r. But when r equals 1, let's put ellipsis points as kind of a suspense instead of a comma. Cosine equals x over 1, which is x, and sine of theta is y over 1, which is y. Holy moly smokers. So on the unit circle, so here's the consequence. On the unit circle, the coordinate xy is really the cosine theta and the sine of that angle theta, respectively. That's the power of the unit circle. The cosine is the x coordinate, and the sine is the which coordinate? Y, which measures the what of the triangle? Height. Sine, y, height. Yeah. And here's what also is cool. I'm going to teach you later, once you know the cosine and the sine value, you can get the other 4 if you want pretty easily. Now, it's pretty easy to remember this because x comes before y in the alphabet. C comes before S in the alphabet, right? X is less than y, and C is less than S in the alphabet order. So if you can't remember sine y, you can just remember, oh, the cosine is the x because C comes before S, and the sine is the y because S comes after C, right? The alphabet order, alphabetized. It's alphabetized, okay? That's awesome. So look at this. This is how we're going to use the unit circle forever, forever and ever. Guess what the cosine of 30 degrees is? The cosine of 30 degrees is, guess what? Square root of 3 over 2. Yeah. And guess what the sine of 30 degrees is always? Always 1/2. Always. And if it works with the radius of 1, as it does, we know that it also works with the radius that's bigger or smaller because the scale factor just divides out. Nice. Nice. That's kind of the whole idea of the unit circle. But let's go. Yeah, sure. Yeah. Let's flesh it out just a little bit more. Let's take that. I'm gonna shade this a little bit lighter. Let's take this right triangle, and you can put a little right triangle symbol there if you want, and let's reflect it across the y-axis. When I reflect it across the y-axis, I get this fella over here, right? And I'll shade him twice to make him a little darker. Okay. Now, when you reflect it, that's called a rigid transformation or an isometry. It means that this triangle is now congruent to that triangle. Congruent means not only are the angles the same, but the side lengths are what? Also the same. The side lengths are the same. So this side length is still square root of 3 over 2, and this side length is still 1/2. But if I want to navigate to this point here, I need to go left square root of 3/2 and then up 1/2. So it's negative positive. So this ordered pair is negative square root of 3/2, comma, positive 1/2. All right. It's the same numbers, but because I'm in quadrant 2, x is negative. Now here's the cool part as well. If I can figure out what the angle is that actually gets me to rotate over to that terminal ray from the positive x-axis, I'll have the cosine and sine for that angle as well. Well, what is it? If this is 30 degrees right here, what's the angle that stops 30 degrees short of the x-axis? If 180 is the x-axis and I got to step 30 degrees short of it, it's 150, right? 180, back off 30 degrees, you're at 150 degrees, okay? And I'm going to get rid of the arc because the arc's going to clutter everything up. So guess what now the cosine of 150 degrees is? The cosine of 150 degrees is Negative square root of 3 over 2 or negative square root of 3 halves? Either one. Either one. And guess what the sine of 150 degrees is? 1/2. Yeah. Sine of 150 degrees and sine of 30 degrees are the same because they're both above the x-axis. Same triangle. Yeah. See how it works? Yeah, yeah. Now, let's take that triangle in quadrant 2 and reflect it across the x-axis. Oh, wrong tool. Here we go. And now we get this guy here, which I guess I'll have to shade 3 times, or maybe just switch to orange. Yeah, orange. Orange. Okay. The side lengths are the same. It's congruent. So it's now the square root of 3 over 2 and 1/2. Those are the lengths. Those are the lengths. But I got to get to this point here, which is in quadrant 3. So I have to go left again by that amount. But now I got to go down. So now the x and y coordinate are both negative, right? Negative square root of 3 halves, negative 1/2. Kaboom. And if this reference angle here is still 30 degrees, what is the angle, the actual angle then that I need to rotate from the positive x-axis in standard form to land at that terminal ray, which is 30 degrees past the x-axis now? Autumn's already written it down. Yeah, and like with Putin, once she writes it down, it's law, right? Yeah, it's what I say. No, you're right. It's 180 plus 30, right? 180 degrees all the way to the x-axis plus another 30, 210 degrees. So watch this. With my eyes closed, I've been doing this so long. What is the cosine of 210 degrees? Negative square root of 3 over 2. Boom. It's the exact same as cosine of 150 degrees because it's the same triangle, 30-degree reference angle, and they're both to the left of the y-axis. What's the sine of 210 degrees? Negative 1/2 because it's below the x-axis. Got it? Yeah, that makes so much sense, right? Unlike attacking Ukraine, I watched the history of it. It's like this. They've done this like through the course since like they were both founded at Kiev Rus, whatever, way back in the. Russia has tried to take Ukraine so many times, and in the late or in the early, I guess it was the early 20th century, they actually went in. They have a name for it. It's like the Ukrainian Holocaust. The USSR went in there and stole their food, deliberately stole their food. And they tried to do genocide by starvation. And like 4 million Ukrainians died of starvation. It was crazy. It was sad. And here we go again. All right, let's reflect that across the, let's reflect the orange one across the y-axis. And we get the last little reference triangle of 30 degrees. I'll do a double orange here. Double, let's do triple orange. I like the contrast just to show some variation. All right. Oh, bubble gum, nice. Now the side lengths are the same because it is congruent. So this is the square root of 3 over 2, and this is 1/2. But to get to this point on the circle, I have to go right, which is positive, and down, which is negative. So this ordered pair is square root of 3 halves, comma, negative 1/2. And if this reference angle is 30 degrees, then what is the actual angle that I need to go all the way around and stop at that terminal array 30 degrees short of a full rotation? 330. Yes. And now, what is the cosine of 330 degrees? The cosine, square root of 3 over 2. And what's the sine of 330 degrees? Negative 1/2. Yeah. It is pretty crazy. And we're going to learn it for the 45 and the 60. There's 4 for each of those. And then we got the quadrantal angles. And it's going to be the same in every case. The x-coordinate represents the cosine, and the y-coordinate represents the sine. And if we can have those memorized, we can then find the other 4 pretty easily. Watch, like for instance, I'll just give you a little taste. What was the sine of 330 degrees? Negative 1/2. So what do you think the cosecant of 330 degrees is? Negative 2. Yeah, buddy, because you just flip it. What would be the secant of 330 degrees? You would flip it, 2 over square root of 3, and then rationalize that. 2 square root of 3 over 3. Yeah, boom, boom. Boom, boom. Hey, look, and what do you think the cotangent of 330 degrees is? Cotangent is x over y. If I take this x and divide it by that y, these denominators of 2's are going to divide out. So it's just like doing square root of 3 over -1. What's the square root of 3 divided by -1? Negative square root of 3. So guess what cotangent of 330 degrees is? Negative square root of 3. And what do you think the tangent of 330 degrees is? Well, y over x, the 2's divide out again. Now it's -1 over the square root of 3, which when you rationalize it is negative square root of 3 over 3. Kaboom, there's all 6. Yeah, oh yeah, oh yeah. Yeah, it is a lot better. Now, here's the deal. Memorizing the angles all the way around is one thing. Those are different numbers, right? 30, 150, 210, 330. You can figure it out. But you want to remember that for those reference angles of 30 degrees, our triangle is wider than it is tall. See that? Because we're not rotated that far off the x-axis. So our triangle is square root of 3 wide and only 1/2 tall. Square root of 3/2 is bigger than 1/2, right? Because the square root of 3 is bigger than 1. So the x coordinate is always square root of 3 over 2 for each of those. And the y coordinate is always some type of 1/2. So if you kind of hold your arms kind of like parallel, right? And then you just do kind of like some 30-degree flaps, right? 30 degrees up, 30 degrees down, 30 degrees up, 30 degrees down. Those are your 30-degree reference angles, right? 30, 150, 210, 330. Those always have coordinates of square root of 3/2, comma, 1/2. And if you know the quadrants in which they terminate, you can assign them positive and negative numbers easily. Yes, yes? And if you can flap your wings really, really fast like a hummingbird, you might need a hard hat because your head's going to bump the ceiling. All right, now here's the best thing. We're going to abandon degrees altogether, and we're going to do this in radians. And it's going to be even easier once we do it in radians. Because it's going to be 1 pi 6, 5 pi 6, 7 pi 6, 11 pi 6. Switching back and forth. And I told you we were going to be done with it, right? Well, I keep trying to tie into what you already know. That's kind of the teaching strategy. All right. Tomorrow we'll review and we'll test Wednesday. Have a super duper awesome rest of your day. Is there a video of this?
Is there going to be a video?
Oh, you're on the video right now.
Oh.
Yeah, yeah.